From the Financial Times in London, I'm Andrew Ward, and this is FT News. It's been described by enthusiasts as the next great frontier in medical science, the potential to harness the natural electronic signals of the nervous system to treat diseases. Some people call this bioelectronics, others prefer electroceuticals. Either way, it's an exciting concept, and I'm here with Clive Cookson, the FT's science editor, to discuss the possibilities it's opening. So Clive, this sounds like science fiction. How realistic is this idea?
It really is beginning to happen. Until now, drug companies and medical science has really worked with chemistry and biology, interfering with the biochemical pathways in the body. It's now becoming possible, I think for the first time, to interfere with the electrical signals. And what's given credibility is one big drug company, GlaxoSmithKline. GSK has really hung its colours to the mast of electroceuticals or bioelectronics and launched quite an ambitious research programme. At the same time, various government labs, particularly in the US, have. There's DARPA, the Pentagon's Futuristic Science Agency, and also the National Institutes of Health. They've got a programme in this area, and between them they're putting a couple of $100 million in.
So give us some examples of their work.
Well, what's perhaps surprising is when you think about bioelectronics, when I first heard about it, I thought they must be working with the brain. But most of this work is not with the brain or the central nervous system. They're working with what's called the peripheral nervous system, which pervades the body. There's an information superhighway going from the tips of your toes to the tops of your scalp. Lots and lots of nerves there, and everything that happens in the body depends on the peripheral nervous system. And a lot of the work is with those peripheral nerves.
As I understand it, there is a key element of the nervous system called the vagus nerve. It's been described as the communications superhighway of the body. Explain how that fits into bioelectronic.
Yes, the vagus nerve is the archetypal peripheral nerve. It's the longest nerve in the body. It connects various organs like the digestive system to the brain. And the idea is that if you interfere with those signals, you may be able to cure some quite unexpected things, like, for example, metabolic disease, digestive disorders. Also, the vagus nerve is involved in inflammatory responses. So it might even be possible to interfere with the process that leads to rheumatoid arthritis instead of giving chemical drugs. Now, GlaxoSmithKline and others are really just at the stage of basic science and animal experiments. There are a few examples of bioelectronics in the body. I mean, the most ancient is the heart pacemaker. But I think the vast majority of this is still to come, and GSK is saying maybe into the clinic around 2020. So given the development times, I guess we're looking 15 years ahead before this really flourishes.
One of the biggest challenges for traditional pharmaceuticals has been breaching the blood-brain barrier, getting medicines into the brain to treat neurological conditions. Could electroceuticals have an advantage over pharmaceuticals in their ability to penetrate the brain and to treat anything from migraines to perhaps even depression?
Very much so, yes. There's a distinction between invasive implants, which you'll actually put some sort of electronic device into the brain, requiring surgery. But I think the biggest hope is that it'll be possible to modulate brain activity through the scalp with various electromagnetic devices. That's certainly very promising for hard-to-treat psychiatric and mental conditions.
We've seen some very exciting examples in the past couple of years of, for the first time, the brain being able to communicate with prosthetic limbs. That's another example of bioelectronics, isn't it?
Yes, bioelectronics could transform the lives of people with severe handicaps. It is possible on a simple, primitive scale already to decode the brainwaves sufficiently to get either a robotic arm or, under some circumstances, your own limb to move. Those movements are very, very limited, but it's moving ahead fast, this field. And it's going to also make it possible, I think, there's a race in treating spinal injuries between the biological treatments, stem cells and so on, getting the spine and its nerves to regrow, and bioelectronics, which will bypass the break in the spine and send an instruction from the brain to the limbs.
So do we need to have implanted devices that are delivering the electronic signals or pulses to the nerves, or could you imagine handheld devices delivering pulses from outside the body?
That would certainly be cheaper than implants, less invasive. I think one of the greatest hopes is for sort of smart skin that you'd stick on the outside of the body, which would give these electromagnetic impulses. But I have to say that there is a danger already that people promising too much are going to ride on the backs of this. There's a lot of hype, particularly about the magnetic stimulation you can give from outside the brain, and people are selling things that claim to do some of these bioelectronic miracles, but aren't really doing them well.
What about the use of bioelectronics to potentially enhance the body, to enhance our physical or cognitive abilities? You can see the possibilities, can't you, Clive?
You certainly can. And one field in which this is going to be a big issue is sports doping. Think what enhancements you could obtain as an athlete through bioelectronics. And with really miniaturized devices, sort of nano-electronics, it might be quite hard to spot.
And what about cybersecurity? If we start to bring together medicine and electronics, is there a cybersecurity risk here? Could we see the spectre of body hacking?
Yes, it's something that the developers of the hardware and obviously particularly the software will have to bear in mind. I mean, like a lot of this conversation, it's quite a futuristic concern, but it's something that needs to be borne in mind as the technology moves forward, yes.
Fascinating science, Clive, but lots of challenges and risks to consider as well. Thanks very much for your insights.
Thanks, Andrew.
From the Financial Times in London, I'm Andrew Ward, and this is FT News.